See how we're doing time-wise. Okay, you can parameterize this by x equals 4 sine pi cosine theta. This parameterization is very obvious if you converse it with polar coordinates. Okay, it's the upper hemisphere, so that it's the whole hemisphere, so you're getting circles in the xy plane, and that's controlled by your cosine and sine of theta, so that theta is going to go from 0 to 2 pi. And you're just in the upper half plane, so your phi, which is your angle with the z-axis, just comes down to pi over 2. If it goes beyond that, you get the lower part of the hemisphere. So if you want to do the whole sphere, that's easy to do. But right now we're only doing the hemisphere, so that phi is going to go from 0 to pi over 2. Then your r vector is going to be 4 sine phi cosine theta I plus 4 sine phi sine theta times j plus 4k. Dispensing with the mapping, well, yeah, I'll just draw it here just to remind you that I really want you to think about it. If you have theta here, phi here, you have this rectangle. Dimensions 2 pi by pi over 2. You partition theta, you partition phi. You take a typical increment and you map it onto the hemisphere. And again, you get some region. And make this yellow. And make this, what did I use? I used orange. Orange. Over here again, you get some region. What's the region going to look like? Well, as theta changes, you're going to be moving this way in the, rotating around the z-axis. As phi changes, you change along a great circle, okay? And I don't want to detail that because there are other things we want to get to, but the region's going to look much like this. It's going to look a whole lot like the one I did before. I think things are going to end up being perpendicular. I think this thing might well end up being a rectangle. Yeah, just because you're rotating about the z-axis, then you're rotating about the origin, your dimensions are going to be dimensions here are delta theta by delta phi. That maybe be a delta theta I, delta phi j, if you go to all the detail. And your dimensions here approximately R theta delta theta I by r phi, delta phi j. And that is, of course, then what you would call T theta cross T phi again, T theta being the same as R theta. I've invoked this R vector here because, again, I think it helps focus us. There's your area, and that cross product is going to end up being very simple. Your T theta is going to have a negative sine theta here and a cosine theta here, nothing here. Your T phi is going to have cosine theta here, and nothing here. It's going to be a very simple cross product that just quickly, intuitively, without thinking it all the way through, I think confirms the fact that this thing is probably an approximate rectangle. Not sure it should be. Okay, but you can work it out. You think about those things. And this comes out much simpler because, of course, you don't have any k component in the cross product, so you don't even really need a determinant to do the cross product. It's going to be a very simple cross product, and you're going to get a very simple result. Okay, I can't go that far in my head. At least not without a good-sized chunk of caffeine in my body. Okay, and even that might not help. Okay, so there we have it.